where you see companies that are predominant now really starting to make the bet that AI can be helpful in their day-to-day sort of operational environment. And so a good example of that would be Netflix, where in 2006, they actually went ahead and kind of outsourced some of their AI through the Netflix prize problem that was eventually awarded in 2009, when a group of Netflix prize problem participants managed to build an algorithm that works 10% better than the current Netflix algorithm. Ever since then, they've gone all in on AI and data science and helping to try to figure out what it is about movies and shows that you like and will bring you back and keep you paying them every single month. And they do a very good job at that. Now, as the Netflixes of the world, the people who were kind of those really early adopters into pushing AI out into operations, kind of the way we know it, started having success, other sort of more established companies started seeing that and identifying that they too decided they needed to get kind of on this AI bandwagon and start really investing heavily into data science and AI, and not just in the lab, but also kind of in an operational context, because efficiency and bottom lines and helping to improve their overall revenue seemed to be within reach. If they could just figure out how to sift through the data to find useful insights along with it. So
hey, Clayton, quick question for you. Do we have slides for the talk today? Did you want to present anything, or are we just doing a talk?
Hold on.
And not that I don't love your radio announcer voice, but if you had planned on having the slide, it might be cool.
You mean like the slides that I was staring at for the last couple of minutes? Oh, yeah. I'm with you. Hold on just a second. My bad. So, okay, is that better? Can you see slides now?
No.
Not yet, but I see watch stream.
Clayton, we could see it a second ago. Yeah, there you go.
So you can see it here, but you can't see it when it goes full screen.
Yeah.
Well, that's fantastic. So, all right. So we'll go with this. If you guys can't see the other for wonderful reasons. So we had companies like Netflix that kind of came in and really started using AI out in operations, and then you had these other corporations that were well-established corporations start to take a look at how they were losing market and revenue share, and how do we use AI to help really push our operations and really push revenue growth on our side. So my favorite example of that happens to be Target Corp, who started their AI data analytics group in the early 2000s. And as you go back over the last couple decades, you can see several quotes by their executive team attributing their strong revenue growth to their analytics practice, which has essentially gotten really good at predicting what you and I and everyone else kind of wants. And therefore influences their buyers to buy things, and their marketers to send out mailers that have a very targeted and direct sort of marketing sales sheets to you. Now, that's all well and good. The problem arises, and has arisen in the last few years, in that these models are now have now sort of propagated out into the business environments and even into your daily lives, right? For those of you who have like Nest thermostats, et cetera. And in a sense, taken on a life of their own, in that the people who built these models, the people who understand the math, right? And the people who kind of understand fundamentally how they work, are not the day-to-day end users of these models, right? And so when a model at Target tells a buyer at Target that they need to order 3 more semi-trucks full of diapers, right? That model and that model developer are not on the hook for that decision, right? Be it good or be it bad, right? If there's a run on diapers, it's great. If there's not a lot of babies being born, it's really bad at that particular time. The person who's on the hook for that bad decision is the buyer, right? You also have situations where, say in financial services, where loan decisions are being handled in some automated fashions, where AI systems are making decisions about whether or not someone should get a loan. That decision On the AI model side, it then has to be filtered through someone who actually has the responsibility for deciding, right, an underwriter, whether or not someone should actually get a loan or not. And when the underwriters are relying on the AI, and when the buyers are relying on the AI, or when a multitude of other people are relying on the AI, the model is simply saying that this is the right decision is not enough. Sometimes because people just don't trust computers, right? And the buyer and the target case may not trust the computer. Sometimes because there's a legal requirement that just simply the AI development has been out of step with over the course of the last few years, right? If someone is denied a loan, they have a legal right to know and understand why they were denied a loan. And so it's in this kind of mix where the reality of what you can do with AI, even when it's working really well, doesn't necessarily mesh with what humans have come to know, expect, and in some cases are legally required to provide. It's at that sort of disjoint that you get to the point that you need an explainability solution in AI. You need a way for you to convey to another human being how and why a particular decision was being made by an AI system when action was taken on that decision, right? Loan approval, loan decline, ordering a whole bunch of diapers, not ordering a whole bunch of diapers. And so that's what explainability is designed to provide. It's that why for AI models where we're at now. So a couple of things with jargon real quick that you'll need to understand. If you don't take anything else away from this particular talk, take away the following. Explainability is all about figuring out how small changes to inputs can drive big changes to outputs. Okay? So explainability is all about understanding which inputs were important to the model and how small changes to those inputs would have changed the model's opinion and the decision that the model's being made, the decision that the model made. And so that's what explainable AI is. For those of you who see the term XAI, it's a shorthand notation. Sometimes you'll see it tagged in articles or in publications. It just means explainable AI. Interpretable AI is a little bit different than explainable AI. Interpretable AI is a subset of explainable AI, wherein the inputs that are being provided to the model are things that you would be normally familiar with, right? And so an example for interpretable versus explainable AI, if I build an object detection algorithm that takes in images and identifies people in the image, then that model can tell you that this is a picture of a person because these pixels here make up a person's face, for example. And you and I would both understand that because we're used to staring at images and pictures, and we kind of have an understanding of what those pixel values mean. If, however, I were to build an object detection algorithm that looked at radar data and told me that there was a plane overhead because of the radar data, it could just as easily provide an explanation that has something to say about the radar signals and their phases and magnitudes and those sorts of things. And mathematically, it would be correct, right? Mathematically, the explanation for why that model said there was an airplane above your head could tell you that it was due to all of these different sort of characteristics of the radar, but they don't mean anything to you and me kind of in our daily experience, right? And so that sort of AI model that uses kind of esoteric things that you're not necessarily familiar with would be explainable but not interpretable, whereas the image is both explainable and interpretable. So with that in mind, let's talk a little bit about explainability. That's what we're going to focus on. Explainability, like I said, is all about identifying which inputs have the most weight on the output of an ML model, right? And that really comes in kind of two dimensions for explainability, right? The first dimension is a simple one that everyone's familiar with. It's kind of the processing capacity required to perform whatever sort of explainability approach you want to take with a model that is processing your data of choice, right? And those methods come in one of two fashions. One is online and the second is offline. We would refer to any method that is capable of providing you an explanation with one single inference as an online method. Okay? So these are methods where you simply run your data through your model, and based upon either the model or the output, it's easy for you to tell what caused the model to make its decision. The second way, kind of the second part in that dimension, is the offline approach. The offline approach, we would consider any model to be offline that requires you to make several different inferences before you can produce an output. Right? So that's kind of the first computational complexity, is kind of the first dimension there for explainability. The second dimension is more of a what do you mean by an explainable model or an explainable solution, where we have what we call global explainability and we have local explainability. In global explainability, what you're doing is trying to explain what the model itself cares about. It's a characteristic of a trained model itself, and it applies to every input that's provided to that model. The second approach, the local approach, local explainability is about explaining how a particular input, what was important for a particular input, output from the model. Okay? So when we talk about the model in general and we want to explain how a model works, we think global. When we want to talk about a particular instance, when a particular instance of a model being applied to data, like say for a loan application, those are local explanations. Okay. So most people are kind of familiar with the idea of the complexity and whether something's online or offline. So we're gonna kind of hold on to that for a second and talk instead about this kind of an intuition for this global versus local thing. So imagine that you are going to try to cross a bridge. It's going to be this rickety bridge that you see here on the screen. And what you are going to do is that you're going to put on a blindfold, and you have an AI system that allows you, that will tell you whether you're going to make a safe or an unsafe step as you go across the bridge. Okay? And so what a global explanation would provide you is an understanding of whether your safety, in this case, is more tied to movements that go left to right on this image across the bridge, or whether they're tied to movements that go up and down and could possibly take you off of the bridge, in this case. And the way that the global explanation does that is that it takes a look at every single spot on this bridge and says, on average, you can take more steps across the bridge back and forth and still be safe than you could side steps that would require you to fall off the bridge, right? So on average, you will be safer if you take steps that kind of move you towards your objective of getting across the bridge, right? Now what that means is that the model is actually more concerned with whether you're taking steps that would let you come off of the bridge to the sides than it is steps that allow you to make progress getting across that bridge, right? Because the steps that would go laterally and push you over the side very quickly take you from a position of safety to one of being unsafe, right? And so a global explanation would look at all the points on that bridge and it would say, in general, moving forward is safe. I don't really care about that. I care if he's trying to step off the bridge one way or the other and kind of fall into this crevice that's sitting here. It's the same regardless of where you are on the bridge. That information is always going to be conveyed the same because it is a property of the model. Okay? Local explainability, on the other hand, would look at these same two locations we have here. It would look at this 8-pointed star on the bottom left corner, and it would say, hey, I can make a lot of movement across the bridge or back away from it without having to worry, but I can only make small movements down or kind of small movements up before I kind of fall off the side of that bridge. So I'm really worried about small movements up and down. In this particular instance, I'm not so worried about movements that take me across the bridge or back, which is in alignment with the global explanation of the overall model, right? But if you take a look instead at this top right star up here, what you're seeing here is that you can make very small movements up before you go from safe to unsafe. You can make decent movements down before you go from safe to unsafe. And you can make a lot of movement backward. But you can't make any movement forward before you become unsafe. Right now you're in a safe position. If you take a small step forward, you're going to very quickly find yourself at the bottom of that canyon. Okay? And so in that local instance, the thing that's most important to the model's decision is your movement forward across that bridge. Right? That's what causes your model to say things are unsafe. And that is a different, situationally dependent answer than the global explainability. So if your concern is, how does my model generally, what does my model generally care about? You want global explainability. If you are concerned about, in this particular instance, right, this particular loan application, then you want local explainability. Okay. And so let's take a look at a few examples, a couple of concrete examples of different approaches and techniques, kind of split along global, local, and online, offline. So an example of a global online explainability solution is explainability associated with a linear regression. Now, most data scientists, AI practitioners, this is one of the first things you learn how to do. You have some value, and it's going to be dependent on some bias, plus some coefficients assigned to your inputs. Now, what we're trying to do is figure out which of the inputs to our model will, with a small change to it, largely affect the output. Right? So we want small perturbations in X to create big changes in Y. Okay? And so if you think about it mathematically, it's essentially a derivative. It's first semester calculus where changes in Y, like change in Y over change in X, and those correspond to these beta values that you see here on the screen in this equation. And so if beta 1 on this equation is really big, and it's 1 million, then a small change in x1 will create a big change in y. Right? And so the value you get out y is your model, right? Like this whole thing is your model. And so a small change in that little input creates a big change in y. Whereas if beta 2 is really small, say 0, right? Then it doesn't matter how big your change in x is, you're not going to affect y at all, right? So the inputs, the x's, the manner in which the inputs affect the outputs can just be read right off of the model. When you do this, right, it actually doesn't matter if the beta is really positive or really negative. You can read them off, absolute value, rank them, and what you're seeing there are the importances of those individual input parameters to the model as a whole. Okay. This gives you, taking a look at those beta values and their kind of assigned inputs, gives you a really good handle on what this model as a whole thinks is most important. And it can be done immediately every time you run a linear regression. And so we would consider this to be a global online example. Global offline example. So linear regression is nice. It gives you an idea of what the regression cares about, but linear regressions are very constrained, right? Because most models that are used in production, most models that are used in machine learning and AI are very nonlinear systems. And so if you want to get a global understanding of what your model cares about, but your model happens to be nonlinear in some way, then there is another alternative, and we call that alternative permutation importance. Okay? And the way this works is that you build your model however you want on a set of training data. And it can be any sort of model, SVMs, random forest, just take your pick, right? And then you have a holdout validation set. And so once you have your trained model, you take your validation set, and you calculate your metric of choice on it. Accuracy, precision, recall, whatever it's going to be. Calculate your precision, your metric of choice, and you use that as a baseline. And you take your baseline, put it over to the side, and then you take that validation set and you pick a column. And in that column, what you're going to do is you're going to scramble up all of the values in that column. So they're just moved to different locations. Right? And then you take your model and you're going to calculate, again, that same metric you calculated earlier. When you look at the final metric that you calculate from scrambling up that column, and you compare it to your initial one, if there's no change, or at least no appreciable change, you know that that column is not important for your model, because you were able to basically just scramble it all up and it didn't affect the performance elements of the model. Conversely, if you were to take a different column and scramble it all up, and the metric value is significantly different than your baseline value, then you know that that column is really important. The way that this is used in the real world is that you take the model, you follow the process I just said, and then you rank the columns based upon how heavily they changed the metric from the baseline metric. When you're done with this, you have a global offline example because the ranking that you have for your input values and how they affect the output tells you about the model, and it has to be done with several inferences, one right after the other. The advantage to this is that it can be applied with any sort of model and not just linear regressions. So as we move from kind of the global to the local example, we're going to take a look here, right? Remember, at not the model as a whole, but for individual instances that are being fed into a model and individual output and the output that those individual instances produced. Okay? And so models, so explainability that is directed at a specific instance we call local. The first example we're going to look at is one that is online. This is an example of Mozi's AXAI explainability capability. If you remember a few slides ago, I made the point that explainability is about identifying small perturbations to input that can have big changes on output. Okay? There's an entire area of AI that is dedicated to trying to identify how to trick a model by doing just that, by identifying what small deviations to input can produce large deviations to output, and it's known as adversarial AI. The way that Mozi's AXAI approach works is that we take an input, we run it through a model, and then after we run it through the model, we perform a slight adversarial attack on it to help us identify which of those inputs were most important or were most easily changed to change the output of the model itself. For people who are interested in the actual technical details of that, we'll put a link in the Tech Talks or the general channel for this afterwards. The important point for its classification is that it happens on a per instance basis, and that it happens and it can happen after one inference, right? So local online example. The image you see here on the right is an example of Mozi's AXAI applied to an image and identifying it as a BMW. If you're interested in that, you can sign up at apps.mozi.com and take a look at the explainability results that are hosted there in that instant. Finally, we're going to take a look at a local offline example. So this is probably the example that most of you have heard about if you've done much in terms of explainability in AI, and it's Lime. Okay? Lime is a very popular explainability capability that kind of sits on top of other machine learning models. And the way Lime works is actually kind of an odd combination of some of the things you've heard about already. Lime takes an instance, right? It's a local explainability capability. So it takes an input instance, and let's say it's that large red cross sitting there in the image on the right. Then it classifies it, right? And so it just classifies it by itself, and in this case, that large red cross would classify it as red, and it holds on to that information. And then what Lime does is that it changes just one or two of the parameters, and then it calculates a classification again. And so it would kind of take that red X and then it would kind of move it around. And maybe it moves it to the right a little bit. Well, if it moves it to the right a little bit, it's no longer red, it's blue. So it's okay, small movements to the right give me blue. And so it records that. And then small movements up keep me red, small movements to the left keep me red, and kind of on and on. And once it has that information about how small movements change the classification, it can build essentially a boundary line that works locally. It's not a global description of the model, but it is a description of how the model functions in that particular region. Right? And once you have that, you can create basically a linear regression the same way we did earlier with the global online example. and then read the coefficients off to identify what the most important inputs happen to be to the classification decision being made right then. I realize that's a whole lot of kind of jargon together, but the bottom line is that Lime will take a model and an input, it'll calculate a value, and then it'll kind of shift that input around so that it can calculate another value until it gets a good understanding locally around the input, how the model is functioning, and then it creates that linear approximation and just reads the coefficients off. It provides understanding of single inputs and single inferences and what's important to them. It requires multiple inferences, and so we call it a local offline example. And so, kind of in summary, why do we have explainability? Why is explainability important? Right? Explainability is important because we are getting to the point where, as humans, we rely an awful lot on AI to help us manage our lives. But that AI is really constrained in what it knows and understands. So we need to make sure that the decisions that we're relying on AI for are taking into account the information that we consider to be important. Explainability at the end of the day, identifying what is important for a model is all about identifying sensitivity. It's about identifying the inputs to the model that small perturbations of would cause a drastic change in the output itself. When people talk about explainability, some talk about global, some talk about local. It's just important to know that there are different types of explainability, and that some are really important for characterizing models, and others are really important for characterizing particular instances. And the last thing I'd say is just to remember the online versus offline thing of explainability, or aspect of explainability. Some explainability methods can be easily calculated, and so they're well suited to situations in which you have to perform a lot of inferences real time. Other explainability methods require quite a bit of additional processing, so that they can come to an understanding of what is causing the model to make a decision as opposed to a separate decision. And so that's pretty much all that we've got to talk about today. So I guess I'll stop here and see if we've got any questions.
Hey Clayton, if someone's coming into explainability kind of cold, brand new, limited experience in that field, but has some model training experience, what would be your suggestions for kind of getting started? Like what would be a good place to go, or good next step to sort of maybe take a crack at using Lime or some of these other kind of standard options?
Yeah, so we can go ahead and put a link or two sitting here in one of the Discord servers, probably over in general, for folks who are interested in getting to know and experience the different sort of explainability solutions that are out there. Lime is by far the most accessible of the explainability solutions, in that it gives people what they normally think about and are wanting to know about when an AI model makes a decision, right? They're wanting to know why this particular decision was made in most cases. And so we'll go ahead and put some links in the Discord channel, especially kind of like the original Lime paper, and maybe some examples as well.
That sounds great. Clayton, thank you so much. This is awesome.
All right. Take it easy, guys.